Hello everyone. Thank you so much for coming tonight. I'm Ashley Zelinskie and this is my exhibition, Unfolding the Universe. So I wanted to give you a little bit of background about the exhibition, and then after we have our two guest speakers talk, I can take you around the gallery a little bit and explain more about the individual artworks. So I've been working with the NASA James Webb Space Telescope team for 7 years now. I was able to see the telescope when it was here on Earth in 2016. I visited NASA Goddard and I saw it in the clean room on the observation deck, did some sketches, interviewed some of the scientists, and that's when I made my first piece, Exploration, which you can see back in this room over here. It's the telescope mirrors, and then it has 3 arms reaching out. One is mine, one is Amber Strawn's, and one is John Mather's. And so after that collaboration, during the pandemic in 2020, NASA reached out to me to ask for help doing some public outreach in a time of COVID when nobody could get together and hang out and see each other in person. I suggested a VR space, a virtual reality world where people could meet, see some art, learn about the telescope, and meet some scientists, and we did some live stream talks. So that virtual reality world is also part of this exhibition, and you guys can try on the headset after the talk, and we can take you through. But that has 12 scientists that I did interviews with. The whole experience is sound mapped, so when you virtually walk up to the portrait of the scientist, they'll give a little clip from the interview, and you can learn about the telescope, and it was really great. And so we had a couple of the scientists that were on that project give live talks we were able to invite people into the VR space on Mozilla Hubs, which is an extremely democratic VR platform. You can access it from your desktop, so you don't need a headset. So anybody with the link off of Twitter could join in and learn about the telescope. They would appear as a little avatar inside the virtual world, as would the scientist, and we'd give a talk. So now we're doing them in real life. We're able to do them in person, and that's how this exhibition came to be. And so since July 12th, when the first images were released from the James Webb Space Telescope, and the world was like, wow, these are so cool, I was able to actually be at Goddard for the first image release, which was really special. And then I went home and got started on this exhibition. So in under 3 months, I produced most of the work that you're seeing here in the gallery tonight. And now that the exhibition is open, we're going to give talks with scientists from the Space Telescope Institute, from NASA Goddard, and from the European Space Agency every weekend until it closes. So please check back. We have an Eventbrite list out in the lobby where you can scan the QR code and come to another talk. So now I'd like to introduce our guests of honor, Joseph and ALYSSA from the Space Telescope Institute, and they're going to tell us about how they processed the first images from the James Webb Space Telescope. So come on up.
Hi everyone. Oh, it's loud. Hi everyone. Thanks for joining us tonight. I'm ALYSSA, as Ashley said, and I work for Space Telescope Science Institute within the Office of Public Outreach with Joe. And as science visuals developers, we create color images from Webb data and Hubble data. But before I get into how we do that, I wanted to give a big thank you to Ashley for this wonderful exhibit, for having us here. Your exhibit perfectly captures the beauty and the wonder of space and space exploration. And this exhibit is a great demonstration of showing that there's so many different ways to explore and appreciate and understand our universe. Whether that be through art, through film, through literature, art and science, of course, and beyond. Now, our job as image processors is to try to take all these perspectives and combine them. Specifically, we're trying to leverage art and science and make an image that's both compelling, engaging, and also informative. And the intention of this is to make these images accessible to everyone and their understanding of the universe. Now, because there is a level of interpretation here, which there is for any sort of photography when you get sort of later into the process, there can be a little bit of skepticism, even though we've been doing this for a long time. Astronomers back in the day actually had to look into the sky with their telescopes, and they had to sketch these images that they saw. And depending on the astronomer, they might focus on something different. Maybe they cared more about the detail and the structure of a galaxy, or someone cared about the overall shape. So it really depended. So this being said, sorry, I'm looking here and this is what you wanted to see before. But we get often a lot of questions of like, is this real? And I can say unequivocally, it is. This is real data. But of course, this is IR. We cannot see in the IR, so we need to translate it into a realm that we can understand. And we get another question is, would it look like this if I could somehow go there? Now that question's a little bit more involved, and I kind of alluded to in the last explanation, is we can't see it, so there is a level of interpretation there. But that doesn't make it any less real. And it's helpful to kind of examine this looking at sort of a parallel science field. And that is through microbiology, except looking at the very micro instead of the macro. But the parallel here is that you need telescopes or microscopes in order to see these things. You need advanced technology in order to observe them. So on the left, unfortunately, is the coronavirus, which I'm sure many of you are familiar with. And it's an image from the electron microscope. It's a grayscale image. This is what you'd see through a microscope. And on the right is probably something you're more familiar with, which is a color image. And it's a scientific illustration, and it's being separated with color. It's separating the proteins and the structure with the color. And you're actually getting a better, more informed sort of intuition here, right? Because this is not only showing the different structures, but those sort of red tendrils that are supposed to attach to your cells, they seem kind of dangerous, right? So it's kind of giving you a little bit more insight to, don't mess with that. And we sort of utilize colors in astronomy the same way. So these colors represent different processes, different structures. And these are actually taken in black and white too, which we'll get to in a little bit. These colors aren't arbitrary. But when we use all these colors, we're actually getting a fuller picture, a fuller understanding. So how do we process the Webb data? So there's two basic things we start out with. One is called image stretching. And it's kind of helpful to look at sort of this video that we have here. Basically, images don't start off in color. The telescope captures them in black and white. And we get color information by capturing specific wavelengths of light through specific filters. And we can see an example here with the light that's being redirected. This is the MIRI instrument, or the mid-infrared instrument on Webb. And you can see it's being redirected through this filter wheel, capturing specific wavelengths of light, and then it's being captured by this detector over here. Now, this is an example with a deep field. It's wonderful, right? Did we make a mistake? No, this is actually how it comes down straight from the telescope. It's completely black, and that's what we call image stretching. That's why it's so important, because the telescopes are so sensitive that we need to stretch the brightness values. We need to scale them up in order to see them, see that detail that's locked away. You can see on the right here the histogram, which represents the distribution of pixel values or brightness values. It's all sort of collapsed on the left side. We want to stretch that histogram out to see more of those brightness values that are tucked away near the dark level. And we can examine this a little further looking at this image of a parrot, which only has 4 values, or 2 bits of information. So we have the black, the dark gray, the light gray, and the white, and we can see its distribution. So how will we stretch this image like we would stretch an astronomy image? So there's different stretches that we can use. So on the left, the far left, that's just as is, 1-to-1, linear. We haven't done anything to this yet. Now we can do a linear transformation if we want to kind of show off those dark gray regions. But here we've sort of manipulated the white point to that gray point, and you see that we've lost all the other information. It's just black and white essentially. So we don't want to do that. We want to do something called a nonlinear transformation, which you see on the right here, where you're sort of showcasing those midtones, but you're still keeping the brightest point. You're not losing any information. And that's exactly what we want to do. So let's look back at the deep field image again, and we can see here, this is a linear stretch, which we don't want to do, and you can see here why, because we're losing all that information on the white point. That's completely gone. You can see the histogram has been stretched, so we are getting more detail, but this is not quite the way to do it. And this is exactly why we do something called a nonlinear stretch. So you can see here is a graphical representation of how that histogram has been distributed better across this sort of scale here, so we can reveal all that information. So that's the first step. Now, we can go a little bit into this further by looking how the Carina Nebula was processed. So again, this is before the images were stretched. So straight from the telescope, different filters, and that's what we get. So we just get black regions with some bright regions where the stars are. And that's after we perform the stretch, where we're revealing that information. This is our nonlinear stretch. So we start to see this structure that's sort of popping out. And that's exactly what we want. So now is the next stage, colorizing the data, or what we call chromatic color ordering. Now, what exactly does this mean? So we can only see invisible light, and that's because the sun primarily emits in the visible. And so our eyes have evolved in order to break down or parse those different components of light. Sorry, I got too carried away. Okay, so as you can see here, the wavelengths that are the shortest we see in blue, so the 440 nanometers, the green 550, and then the red 700. So the longer wavelengths we perceive as red, and the shorter wavelengths we can perceive as blue. And so we keep this relationship for IR. So the longer wavelengths, we're just essentially translating or shifting that information into the infrared, keeping that relationship and that chromatic ordering the same. And you can see that here. With the IR data, we're prescribing the shortest wavelength, the blue, and so on. So you might notice it looks like there's an outlier at the bottom here, and I can explain that. So this is a 470 narrowband filter that's actually just capturing a very small region of emission, particularly hot hydrogen gas. And we can get away with this assigning this yellow because we can see this emission in the 212 wavelength as well. And we do this not only because it doesn't break anything, but we actually get to see that. And that's the whole point of making these images, is to really differentiate between these different filters. Okay, now before we combine all those color images together, we need to start removing things like artifacts. And artifacts just means things that are intrinsic to the observation, the detector, not something that the object is showing itself. So we have some sort of striations that are kind of hard to see, which is sort of electric readout noise from the electronics, essentially. And then we also have this saturated star core, so we need to remove those. And we get like a cleaner image. That's the phase. But once we've done that, then once we prescribe all the colors, we can combine it, and this is sort of our first stage, when we have sort of white balance the image and neutralize it, or color balance the image. It's a little bit difficult when we're dealing with nebula, because in sort of other images like the deep field, you have a sky that you can neutralize as your background. So that should be your frame of reference. In this case, we're using the core of the stars to act as our white point like a photographer would. Now, there's no clear point where this becomes or transitions from an objective process to a subjective process. It's kind of like a balance between the two, and we're evaluating the art and the science simultaneously. But there are definitely aesthetic principles that we consider and are applied to most astronomy images, including things like clarity and color, which are supposed to enhance those details and structures we see in the individual filters, and things like composition and making it evocative. We want it to be interesting, we want you to be engaged, we want you to learn something from these images. So 2 of these things I've actually already done, and that is, I removed some of the artifacts here, but I kept the diffraction spikes. And you'll see that a lot of astronomy images keep the diffraction spikes. Why do we do that? That's actually an artifact of the telescope we're seeing. It's an interaction of the light from the stars on the hexagon mirror and the struts of the secondary mirror. But we keep them because it's almost like a whimsicality. It adds like a little twinkle. Even the star shape that we recognize sort of has this sort of like pointed spikes to it. So that, and it also acts like a Webb signature. So we know when we're looking at these images what took them. also, you've probably seen this image pretty much in this orientation, for the most part, and definitely in this orientation throughout this presentation. But why? Because actually, the north up convention of astronomers, it would be this way. But that looks a little weird, right? Now, there is no true north up in space. So we can really put it any way that we want to that best sort of showcases the data. But why do we choose sort of these landscapes? And Dr. Elizabeth Kessler, an expert on cultural or visual culture of the 19th and 20th century, compares astronomy images to Western landscape paintings and how they evoke the sublime. And I think that's like a very great comparison, because at this time, they were still exploring. There was a lot unknown. There was pioneering that was happening. And so it was full of wonder and awe. And that's what the sublime is. It's generating a sense of awe and wonder. Now, it's twofold. Sometimes it can be transcending the mundane, and it can also evoke senses of fear, depending on who you ask. Now, we're not trying to evoke a sense of fear, and we're not trying to make you feel small. But we're definitely trying to generate a sense of awe and curiosity. And the way that we sort of counteract that sense of fear is to actually use landscapes to make it more relatable, more connected. So you can see here there's parallels between these two images, right? So on the right we have the cliffs of the upper Colorado River. Actually the name is the same too. This is the cliffs of the Carina Nebula. And on the right you can see the erosion of these mountains. And then on the left, and by comparison, you can see the erosion of this dust that's done by these radiating stars. So this comparison makes you feel connected. Now let's go back to sort of this image here when we first combine the full color. Now, I think a lot of people would think, oh, this looks cool, but I feel like we can do more with it. And this is where we're sort of addressing that concepts of clarity and evocative and making it feel more natural. Because to me, this seems a little bit red and teal, which is cool, but maybe not something you can really relate to. And so this is where, so that was very quick. But this is where it kind of gets shifted to a realm that feels a little bit more relatable in the sense that maybe that's like more of an orange dune-scape. And then now you have sort of this contrast between these dunes or these mountains to this more royal blue sky. And that really starts to feel like a mountain. And so I go even further because I'm really trying to emphasize the different structures and the different phenomenon happening here. And we get here, which feels like it's gone a little bit too far, which is not usually the case with astronomy images because, you know, it's like hard to kind of get that color out there. But here I'm like, okay, I think I went a little too far. Let's take it down a notch. And so at the same time, I'm also trying to emphasize the structure in this mountain region. And this is an iterative process with the scientists at all times. And they were saying how we kind of lose that sort of structure and it's sort of overshadowed by that dust, or the gas, I should say. And so we really want to separate that dust and gas region so it really looks like a mountain in the sky. So after all these things have been considered and all of this has been weighed, this is what we end up with as our final image. And thank you. And so we really are trying to capture that sort of spirit of the 19th century landscape paintings, where it's a time of pioneering and we want to create a sense of wonder and curiosity and understanding the unknown, which now is space, like the final frontier. And this is just one representation or one interpretation of this data. This is near-infrared data, but there is a lot of interpretations and there's more data that goes beyond the near-infrared, or there's visible that we can explore, which I'll let Joe get to after the break, I think. Thank you.
Thanks, Ashley. Thanks, everyone, for being here tonight. Thank you, ALYSSA, for that awesome start to this presentation. I'm going to pick up right where ALYSSA left off and talk a little bit about the cosmic cliffs of Carina. But what I want to do is talk about the second set of data that we took of this region of space using the MIRI instrument on Webb, which is the mid-infrared camera. And that is this field here. Now this is a little misleading because this is actually a combination of both NIRCam and MIRI. And there's an interesting story that speaks to the aesthetics of this image behind how it was created. So as ALYSSA was explaining, we use this chromatic ordering of color for all of the data that we put together to make these color images. In the case of a combination of NIRCam and MIRI, we have a lot of data to work with. In this case, 3 filters of NIRCam and another 4 of MIRI. And so if we were to use the chromatic ordering to produce an image using both cameras, you can see that most of the blues and greens end up in NIRCam, and everything else, yellow, orange, red, ends up in MIRI. That actually ends up producing an image that is less than aesthetically pleasing, I think. Now there's an interesting astrophysics in this image, which is unfortunately obscured a little bit in the version that we released, but for the aesthetics, I think it was worth it. What we can see here is that in near infrared, there are a lot of stars that NIRCam picks up. If we go back to, actually I'm going to jump back for a second, because I want to talk to this slide here. Sorry, that's not on the screen. Okay. We'll let the sun come back up. Here we go. Okay. So we're looking at the sun, the emission spectrum of the sun, right? These are the wavelengths of light that the sun emits. This is getting into infrared right around here. Our eyes are sensitive to this, just past that region. This is infrared light. And notice how the curve is just dropping off, right? The sun doesn't emit a lot of light in mid-infrared. And it turns out a lot of stars are like that. So I'm going to jump back to our other slide. Oh, that is not what I wanted to do. Hold on a second. Okay, here we go. Thank you. Okay. Right, so in the MIRI wavelengths, there's not a lot of light coming from the stars that we see in this image. And so when we do a color combination in the chromatic ordering of NIRCam and MIRI, what ends up happening is we get a lot of blue stars that are just pure blue, or a combination of blue and light blue. And then the rest is just, where they match up, we get white stars. And of course the gas clouds come out turning kind of green. So in terms of aesthetics, this image has some issues with it. Now I didn't really explore taking this much beyond this point, because I saw this and I thought, this is going to be really difficult to work with. I think we can do something different with this. Let me start by just making a color image with just the MIRI data and see what that looks like. So we're shifting MIRI over, and now we're using the chromatic ordering just in the MIRI channels. And so the shortest wavelengths of MIRI in this case is purple, and we go to blue, green, and red. And this is the image that comes out of that. Now when I saw this, I was shocked. I love it. But we wanted to do something more with it, because there's just so much there in NIRCam that is not captured in this version. But when I saw this, I was taken aback by, this is a familiar and yet unfamiliar landscape. As Alyssa was alluding to, it very much looks like a landscape. And it reminded me of Claude Monet's series of paintings of the Rouen Cathedral in Normandy, France. He went to this region and he painted this cathedral over 30 times in all different lighting conditions, trying to capture the essence of the scene in front of his face. He was obsessed with capturing it exactly as it appeared every time he painted it. And so we see, he painted it in the morning, he painted it in the afternoon, the harsh light of the afternoon, the beautiful golden hour light of the sunset. It's all captured in this whole series of paintings. And so I thought of that when I saw this MIRI image, because this is like the sunset, the moon shining on the mountainside, and we see, the red sky used to be blue is now red. It seemed to me very much like that series of paintings. And so I thought then, what could we do to combine the beauty of NIRCam and MIRI into a single image? And that was when I came up with this idea that we called Near-MIRI-Cam, which was to interleave the different channels of MIRI and NIRCam together. And so what I mean is that the shortest wavelengths of both NIRCam and MIRI are blue. Then we go into the greens and reds, and we assign those colors accordingly. So it obscures a little bit of the astrophysics, because now you see that there are stars all over this image. And so that fact that stars are not emitting in mid-infrared is kind of lost here, but there are still astrophysically relevant points to this image. This region right here, especially, there's information that's revealed here in mid-infrared that we don't see in the near-infrared. There's a star right here that is in the process of forming. And when stars go through this process, they have these jets that they shoot out. They're emitting material sort of above and below them. And so this star here, right there, is emitting these jets and causing this bow shock to form in this direction. So this jet here is plowing into a dense region of this gas cloud. But there's an opposite jet going this way that actually punches a hole through the gas cloud right here. And you can't see it in this image, but there's actually a little bullet of material, something like up here in the near-cam image, that came from that star. But because it only has this little bit of region to get through, it shoots out and then it takes off. Whereas everything else in the other direction gets kind of plowed into the existing material, and we see these bow shots as a result. Okay, let's move away from the cosmic cliffs of Carina. We're going to take a little trip and we're going to go to the Tarantula Nebula. This was another of Webb's first images. This was actually the first data that we took for the first images of Webb. So this was the first time that we had multiple filters of data and could make a color image from Webb data. And I had the great honor of actually pulling this image together as that data came down, and that was just a career-defining moment for me. It felt like everything's working. This is amazing. There was some speculation about how would colors look in Webb data, how good is it going to be compared to Hubble. All of that just washed away. All those concerns, it was no longer a concern at all. I saw this image coming together on my screen and I was just shocked and in awe. It's beautiful. And this is a really interesting region in space. This is actually outside of the Milky Way, so we're a little further away in a neighboring galaxy of ours called the Large Magellanic Cloud. It's about 170,000 light years away. What we're seeing here is a cluster of hot young stars. That's why they show up blue here, because they're very young. They're emitting a lot of light in the near infrared. So in the shortest wavelength channels that we color blue. And they're actually sculpting this entire environment. They've created this cavity here. Their winds have blown a bubble, essentially. And that's what we're seeing as the result of all of those winds collectively creating this giant bubble and shaping the whole region of space in this area that we call the Tarantula Nebula, or 30 Doradus. Now, as this image came together, I'll admit I didn't think of this myself, but had some conversations with some other people about it, and they were like, this looks a lot like Renaissance painting, like the old masters, like Caravaggio. So I did some research, I looked up some Caravaggio paintings, and I started thinking, yeah, I can see that, right? There's a lot of darkness and there's a lot of light. It's defined by the darkness and the light. This painting on the left is the calling of Matthew and Narcissus on the right here. These were both painted around 1600. But the one that really spoke to me was the beheading of Holofernes. And then, despite the macabre nature of this image, the colors and the light in this image really spoke to me as being a direct comparison to the Tarantula Nebula. And also, Judith's face here, it's like, she looks like she's looking at a Twitter thread, and she's just really disgusted by it, right? Like, she's cutting someone's head off. I would think she'd have a different expression. Anyway, let's go back and start breaking this down the way ALYSSA did with her Carina Nebula. We're going to break this down into its color channels. So we're going to sweep it out, and we'll look at the individual colors. ALYSSA showed some of these channels as well. These are, again, the filters on the instrument. So F090W, that just means we're looking at light at around 900 nanometers, 0.9 microns. These are the technical terms for this stuff. The W just means that it's a wide band filter, so it takes in a large swath of infrared light centered around 900 nanometers. And this is just beyond human vision, so this would be just beyond the reddest light that we can see with our eyes, and really we'd be perceiving this as heat. 2 microns here, 200 nanometers, not 200, 2000, sorry, 2000 nanometers. This channel is actually really interesting. We're going to dig into this one a little bit in a second. And then, of course, the longest wavelength is red here, 4.44 micron. Now, of course, these come down in black and white, so we can actually see them a little better on the screen here in black and white. And I want to focus in on this F335M image because it looks so different from the other ones, right? There's a reason for that. This is actually a medium band filter, so it's taking in a smaller swath of infrared light. And we've done some processing on this to even hone in more on that specific wavelength of light that it's looking for. So what I have here is, oh, sorry, we'll go back. Nope, that's not what I want to do. Sorry.
Good luck.
Yeah. Where was I? Here we go. Okay. The back button was going forward. Okay. So F335M, this is a medium band filter that actually takes in a little bit of extra light. And so we can do something called continuum subtraction using a filter that's nearby in terms of the wavelength, which is the 2 micron filter here, F200W. We actually subtract 200 from 335 to get this. And what this is showing us is really just honing in on the light of what we call PAHs, or PAHs, polycyclic aromatic hydrocarbons. And this is a very gross oversimplification of what that is, but it's essentially soot in space. It's just really, really tiny particles of dust. And in this region of space, they're absorbing ultraviolet photons from those bright young stars and heating up. And it's that heat signature that Webb is seeing. And by doing this subtraction technique, we're just focusing on just that light itself. So that's what we're seeing in this image. Going back to Holofernes, we'll break this down into its color channels. And you can see, by doing that, in the red channel here, that the drape in the background really shows up well because it's very red in the painting. So let's hone in on the red. Now imagine, this is just the red channel. What if we had a camera that could just focus in on the light emitted by blood? That's essentially what we're doing with the narrowband filter on the Tarantula Nebula. So we'll bring everything back together. These are the color channels of that image. This is actually what the image looks like, similar to what Alyssa was saying earlier with the Carina Nebula. This is the starting point. And for me, this is the point where the process becomes a lot more subjective and the art creeps into it. There's decisions that are made about how to represent this region in space, to pull out the most detail and to show off the color separation, get the tonality right, get the color balance right, the white balance, the background, all of that stuff. And so through the process of doing that, I don't have as many steps as Alyssa does here, but I'm just going to jump from that point to the final point. Now I could give an entire talk about how I did just that. But it's basically just lots of curves adjustments in Photoshop, color balancing, getting the background regions like in here, down here, and up in the corner there. I strive for a neutral background, so something that's basically a neutral gray as the background, and then bring that down in terms of its brightness. So getting that color and tonality is like a really important part of this process. Okay, so I'd like to take a step back now and just ponder a little bit about why do we do this? Why is this important, right? There's the obvious answer of putting these amazing instruments in space like Hubble and Webb gives astronomers the ability to answer the questions that they need to. It gives them the tools they need to answer those questions. But that's not it, right? I mean, we wouldn't be standing here looking at Ashley's art if that were the whole goal of the thing. There's more to it than that. These images speak to something deeper inside us. So let's consider scale sizes in the universe. Okay? I see a tendency in people when they look at these images to sort of give in to despair, or ennui, if you want to say that, about the insignificance of our existence in the universe. We are these infinitesimal specks in an indifferent universe, right? That's one way of looking at it. But think about scale sizes. Let's actually break this down. If you were to divide a human in half over and over again, not talking about Holofernes, but just in terms of scale, make someone half the size they were, and keep going and keep going. It would only take about 30 divisions to get to the size of an atom. So that's interesting. Now, if you were to go the other direction and double the size of a human over and over again, it turns out it only takes about 33 doublings to get to the size of the sun. So that's an interesting little fact there, that we, in terms of scale size, we sort of sit right in the middle between the building blocks of all matter and some of the largest structures in the universe. Well, not the largest structures, stars are not the largest, but very large structure, our sun, bigger than all the planets in our solar system. Now there's also the fact that we have over 100 billion neurons in our brains, right? And it also turns out the Milky Way galaxy and many other galaxies have about 100 billion stars in them. So literally, as you're walking around in New York City, every person you walk by is a galaxy in themselves. Their brains are just a galaxy of information. Now these facts, taken on their own, they're just interesting factoids, make you think a little bit. When you think of them in terms of these images and the impact these images have on us, it sort of puts it in a new context. You've probably heard the Carl Sagan quote that we are star stuff before. And where that comes from is the fact that the Big Bang was the creation of everything in the universe. All matter in the universe was contained within the singularity that became the Big Bang. It was in the form of hydrogen and helium. And it just so happened that the universe expanded so quickly that as that heat, that intense heat of the universe at the beginning of the universe dissipated so quickly that the only elements that were able to form were hydrogen and helium. And so the first stars and galaxies that formed were formed from this primordial soup of hydrogen and helium. Those first stars that formed, it was in the process of them going through their life cycle, burning hydrogen and helium into heavier elements, and becoming supernovae. In the process of becoming a supernova, it actually produces more and more heavier elements. Turns out those are the elements that make up all matter, right? Oxygen, magnesium, silicon, sulfur, all of the elements that make us up. The iron in our blood literally comes from forged in the cores of these first stars. And so when we look at these images like the Deep Field, Carina Nebula, Tarantula Nebula, we're looking at the raw materials of us. And I feel there's a deep connection to all of us and to trying to find the answers to the big questions about where we come from, how we got here, and where we're going. And so I feel like instead of giving into despair when you look at these images and thinking of it in terms of the insignificance of our life in the universe, it really is a window into the connections that we all have together. We are all galaxies. If you've ever seen images of the large-scale structure of the universe and the distribution of dark matter across the universe, what you end up seeing is that there are these lanes where galaxies form, and the intersections of those lanes are galaxy clusters. So everything is truly connected from the grandest scales you can think of all the way down to us. We are all a part of this. And so as we look at these images, that's the key thing I think is important to take away from it. We are all connected, and we're a part of this. Thank you.